In lecture 25 today, we're going to start off looking at Mathematica, something I haven't shown you yet in Mathematica. Using Manipulate to make an interactive cylinder, not just making an animation of a graph, but animating like a cylinder, making it get bigger, either wider or taller, and that kind of thing, as motivation to perhaps use such interactivity for your project. I'll do another cylinder area minimization problem, this time without the top to the cylinder, so it's like an open can. We'll look at a practical geometric optimization problem. We're going to be looking at a problem where we're trying to minimize a certain distance, but we'll have a practical application in this case. And then in lecture B, we'll get back into differential equations and look at three models: exponential growth and decay, Newton's law of heating and cooling, and logistic growth. So let's start with Mathematica. So again, you're using this for your project. You are writing your project report in Mathematica, like the project sample report that I sent you yesterday. And you want to use it to do calculations if necessary and make interactive diagrams, whether those be graphs or perhaps geometric objects, making interactive geometric objects in Mathematica. You still end up using Manipulate. There's another version of Manipulate called Animate that can be used as well, but let's focus on Manipulate, keep it simple. And then there's this command called graphics. And you can always find examples of these different kinds of coding by going up to the help menu there and going to Wolfram documentation. And what you would want to look up, and you may want to write this down, is a command called graphics. I just type in graphics there. And what you'll see are some examples of how to use graphics to make various things. You can see what's made here is a disk, a circle, and it's filled in, a square, a circle that's not filled in, a triangle. And actually, in this help menu, you can even make modifications to these things to experiment with them to see what they do. For example, if I want to get rid of that green rectangle, I could cut out this stuff right here that says green rectangle, make it bigger. I could cut this out and re-enter it. Make sure there's no commas right next to each other with nothing in between though. Enter that and the green rectangle went away. I could get rid of the, I could make the circle blue instead of red. Or excuse me, red instead of blue. Okay, that changed that circle from blue to red. I could make the disk blue instead of red. Let's see here. The disk is the first one here. You see a disk. I can change this to blue. Okay, so you can experiment with this thing, and this can make geometric objects. Another version of this called Graphics 3D can make three-dimensional geometric objects. Some examples are here. So here you have like a, looks like a sphere, a red sphere, and a blue cylinder. Hey, I'm going to use cylinder here in a minute. And a green, what is that? Where's the green? It looks green to me. Cuboid is essentially a box. That's the green box. And a yellow polygon, that's the rectangle down there. And again, you can make modifications to these things to see how it affects things. For example, if I change this polygon to having a corner in a different spot, change this -3 to like a -2 or something, it should change that yellow polygon at the bottom, make it a little bit different. Okay? So you can modify these things and see how changes happen to help you make them on your project if you like. Let's go ahead and make an interactive cylinder. Actually, let me go back to the help menu and look up cylinder. So this gives me more detail about cylinder. And if I look at the syntax here for how to use it, this kind of syntax makes a cylinder of radius r, so whatever number you put there is the radius of the cylinder, around the line between 2 points in three-dimensional space. So you see 3 coordinates in each of those points. And so, for example, we see an example here. Let's look at this second one here. So this is a cylinder of radius 1/2 that starts at the origin, that's probably the bottom left point in the center, and goes to the point 1, 1, 1. You could re-enter this, it doesn't affect it, but if I change one of these numbers, like change this to a 2, 1, 1, then it changes the orientation because the second point it's going through on the right side here is a different point. I can change its radius from 1/2 to 1, it makes it bigger radius, that kind of thing. I could, for example, put this kind of thing inside a manipulator. Let me go back to our original notebook. And you can copy and paste these things. And by the way, when you make changes in this documentation center, it doesn't save your changes, so don't worry about that. I can copy and paste this down here, say, and let me make it interactive. Let me put it inside of manipulate. But I need an animation parameter. How about if I change the radius? Allow that radius to change. So instead of putting it a 1, let's make it an R for radius. And then here after the comma, in curly braces, put R, comma 1, comma 3 or something like that. So what that's going to do is that's going to make a cylinder starting at the origin and going through that point at the other end of the cylinder of radius R as R changes. Now, I'm not sure as I change the animation parameter if we're going to actually see the cylinder change, and that's because Mathematica by default sometimes adjusts the viewing window. I guess we are seeing it change. It is adjusting the viewing window, but it's not clear that it's just making the radius bigger. It also seems to be making the height smaller. That's actually not the case because there's nothing in here about the height. In fact, the height would have to be the same because it's going through these 2 points still. So what's happening? Why is it making it seem to change the height as well? I need to fix a plot range. It's changing the plot range as I go here. And to make that change, I think I have to put this inside curly braces here. And outside the curly braces, I can do plot range, arrow, and I wanted to keep it fixed. So I could go like from, maybe -5 to 5 in the X direction, in the Y direction, and in the Z direction. That'll keep the window fixed. And if I do that, now we see it's truly only the radius that's getting bigger and not the height. I could make the height bigger as well by, for example, let's change the orientation of this thing. Let's make it go through 0, 0, 1, so it's sort of standing up vertical like that. I could make the height change as well if I change this 1 to another. That'll make a cylinder whose radius increases and whose height increases as well, and in fact whose height equals the radius. Okay, so there's an interactive cylinder where I've changed both of those things, and then you can look at it from different views. So I'm just trying to give you food for thought for different possible things you can do in your project to get some interactivity, to get some extra credit. Right? I'm looking for some interactivity in order to get some extra credit in the project. And it takes some experimentation. Okay? Nobody knows Mathematica by default. Okay? You've got to experiment. You need to take what I've said and put it into practice. Look at my examples. I put these things in the shared folder. And again, look at this documentation center and look up things like cylinder, or how about cuboid, because that'll make boxes. Okay? If you're interested in making a box or something for your project. There are lots of different possibilities. I'll show you more of this a little bit each day. Okay? I would highly suggest trying to solve your project before Thanksgiving, including maybe making any manipulates you have. And then after Thanksgiving, you're just finishing your write-up. So make sure you fully understand it. You could try to completely finish it before Thanksgiving as well. Let's not do it until the week after Thanksgiving. Can I clarify anything there? Or do you have any questions about the project? This goes for future students as well. Yeah, question?
Is there a limit to how many people can do?
Limit is 4. All right. So that's more manipulate in Mathematica, making an interactive cylinder. Let's do another cylinder surface area minimization problem. What if the cylinder is open? What if it's a can where the top is open? We saw that if it's a closed cylinder, when the volume is fixed, the height and radius that minimize the surface area are such that the height is double the radius, which means really the height and the diameter are the same. The diameter across the top of the cylinder. But what about if you take the top off, making it an open cylinder? what are the dimensions that minimize the surface area? And I'm just talking about the outer surface area, so that would be the bottom of the cylinder and the sides, not the inside. I'll do it on the board here, okay? I don't have anything for this problem on the PowerPoint. So once again, V is fixed. I can once again call that V of G of H comma R. The formula for the volume is the same. And I can set that equal to a constant. I could pick a particular number, but I want you to be able to handle arbitrary constants. That's really important to me. And in fact, again, I've emphasized that's really the key to the most important applications of calculus, is being able to handle situations with parameters. That's what gives you problem-solving power, and it also gives you insight into generalities that you don't make. You're really solving infinitely many problems all at once. It's amazing. The surface area now has a formula that's a little bit different than before. This is without the top. The surface area around the side is still 2 pi RH. Right? The circumference of the top times the height is the surface area around the side, and you can derive that by imagining cutting the side of the cylinder and unwrapping it to look like a rectangle. The height would be h, and the base would be the circumference of the original circle, 2 pi r. However, the surface area that's left over is just the surface area of the bottom. So instead of 2 pi r squared, I just put pi r squared. That'll just be the surface area of the bottom of the cylinder. I'm not including the top now. So it's a slightly different objective function. The constraint is still the same. Constraint, I'm putting these in the opposite order that I did before. But the objective function is different. I would still solve the constraint equation for h in terms of r. C over pi r squared. That's the same as before. When I plug this back into this function, though, in place of h, I do get a different phi function. I'm calling it phi just because I needed a different letter. Okay? And this is actually a common letter to use in many situations, including with differential equations, as we will do in lecture B. Again, you can call that phi if you prefer. Usually, like with fraternities and sororities, they call it phi. But I like saying phi. That's the function you get when you replace h with c over pi times r squared in the formula for f. Okay? It's just, I mean, in a sense, I could have called this f. I'm just using a different letter to emphasize it is, in a sense, a different function, but it's related. And I'm putting the subscript there to emphasize I got this constant. That, in the end, I might be interested in seeing what happens as that fixed volume changes. That's the most interesting thing. Okay? That's the most insightful thing, is to see what happens as c changes. And you, in Mathematica programming, as I emphasized last time, you got to have the c there, because Mathematica doesn't know it's a constant. You are thinking of it as a constant. Plug it in here. I think I'm going to switch the order of these things. Pi r squared plus 2 pi rh, where h gets replaced by c over pi r squared. This part's the same as before. The pi's cancel. One of the r's cancels. So it's a very similar function to what we had before. The only difference really is it's a 1 there in front of the pi, not a 2. It's just pi r squared there instead of 2 pi r squared. That's the only difference. But it is a different function, so we should get a different answer. What's the next step for our optimization problem? What should I do next? Say it louder. Take the first derivative. Differentiate this function with respect to r. You could write it as df dr You're going to get 2 pi r. Before we got 4 pi r there. Now we're getting 2 pi r. And again, it's probably easiest, I mean, you could use the quotient rule, but it's probably easiest to think of it as 2c r to the negative 1 power. So I get minus 2c r to the negative 2 power. Set that equal to 0 and solve for r. The 2's can go away, they cancel. You can also bring this one to the right side by adding it to both sides. And maybe I'll put the r as an r squared in the bottom like that. Then I would multiply both sides by r squared and divide both sides by pi. To get r cubed is c over pi. With the other problem, what we got, there was a 4 pi there, and a 2 pi r there. We had a 2 pi in the bottom before. R is going to be the cube root of c over pi instead of the cube root of c over 2 pi, like we got before. So that should be the, say in centimeters, the radius that minimizes the surface area, though to prove it's a minimum, we have to use the first or second derivative test. We can quickly use the second derivative test. And that's usually what's easier when you got, especially when you've got arbitrary constants c in here, because it's more difficult to think about how the first derivative changes sign when you've got c in there instead of numbers. The second derivative is definitely positive when r is positive. Since c is positive, c is a volume, it's got to be positive. That thing's positive. R to the negative 3 power is not negative, it's positive. It's because it's 1 over r cubed. So that means the graph of phi is concave up. When r is positive, there will be a min at the critical point. Just give that amount of reasoning if you want. It's the second derivative test. So it does give a min. What's the corresponding critical value of h? So this is the critical value of r. I could call this r crit if I preferred. I could even emphasize it depends on c to call it a function of c. All I'm doing there is just emphasizing that it does depend on c. And I could think of it as a function of c if I wanted to. And I do want to often. To find the corresponding critical value of h, h crit of c, say, is going to be c over pi r squared, where you plug in r crit for r. So you got to square this thing. And you got to be careful with this. It's easy to make a mistake. Cube root is the same as 1/3 power. I'm squaring that, so I really get a 2/3 power here. C over pi to the 2/3 power, which is the same as c to the 2/3 divided by pi to the 2/3. That'll be c to the 1/3 on top divided by pi to the 1/3 on the bottom. Cube root of c over pi. This is telling me that when you take the top off, the dimensions that minimize the surface area is not when the height is double the radius, but when the height equals the radius. Before, the height equaled the diameter to minimize the surface area. When you've got a top included, the minimum surface area is with a can like this, where this and this are the same. But now, when we do not include the top, the dimensions that minimize the surface area are when the height is equal to the radius. So it's got to be more squat like that. That's where the height is going to equal the radius. Even less like a soup can, actually. More like a tuna can. Now again, in real life, when you've got soup companies, like Campbell's or something, making these cans, they're not necessarily trying to minimize the surface area. They might be trying to minimize the cost, and they have to take into consideration the cost of the metal, the cost of the welding. And there's also an aesthetic. They want to please their customers based on expectations about how soup cans and how tuna fish cans should look. You know, if they look wrong to customers, then they don't buy them. It's like, why does this soup can look like this? So there's not just minimizing surface area considerations in real life. There are other considerations. Do you have a question? No? Okay. What is the minimum surface area itself? I'm not going to take the time to do it, but the minimum surface area, you can call it S min of C, would be found by plugging, well, you can either just plug R into phi, or you could plug both R and H into F. Either way, you should get the same thing either way. It's probably easiest to plug just the radius into the phi function. You'd plug it into this formula right here, in place of R, and you'd simplify. Okay, you'd get something that depends on C again. That's why I'm emphasizing, you can't quite see it over there. I'm emphasizing these things depend on C. Okay? Again, initially C is constant, but at the end you can think of C as a variable. And then you can manipulate animations of the graphs and see how the minimum point changes as C changes. You could even compare the graph of the surface area as a function of R for this example compared to the previous example. You could put both graphs in the same picture. That'd be pretty interesting too. This kind of thing gives you problem-solving power and insight into what's really going on. Most of the problems that you do from the book, not all of them, but most of them involve particular numbers. Some of these involve parameters. By the way, I'm not explicitly, when I'm talking about this stuff, necessarily talking about the examples in section 4.4, which is titled Families of Functions and Modeling, but I am talking about things that are related. These are really families of functions. Phi sub C of R, it's a family of functions, one function for each value of C. You're studying infinitely many functions all at once. It's amazing. Okay. So I am talking about 4.4 now in a sense, even though I'm not explicitly doing the example. You should study that section and you'll have some problems from that section as well. I'll continue talking about it in lecture B with differential equations. And we'll continue talking about section 4.4 a lot. Pretty much each lecture, something relating to section 4.4 comes up. It's a really important topic. Here's a geometric optimization trying to minimize a distance. That's somewhat practical. Somewhat. On the same side of a straight river, okay, the impracticality is the fact that this river is straight. Okay? No river is really straight, but some rivers are approximately straight. This is the river, by the way. Maybe I should have put the word river in there. I made it blue, right? Because water's blue. Did I tell you about my art teacher? Did I tell you that story? When I was in 8th grade painting, I was painting a picture of a fisherman catching a fish, and my teacher didn't like how blue I made my water. It's like, Kenny, what color is water? And I'm like, not knowing what to say. He's like, come on, Kenny, what color is water? And by now, everybody in the class is looking at me. And I'm like, blue? And he's like, no, water's clear. And everybody laughed at me. And I'm like, well, I thought he wanted me to actually say a color. Actually, in recent years, I looked it up. Water actually does have a slight bluish tint to it. So I should, he might not be alive anymore. Usually it's just reflecting the sky, right? That's the usual thing, but that's why it looks blue. Anyway, that's water there. That's a river, okay? You got two towns, town 1 and town 2. You're going to have a problem like this for the assignment due Friday, but you'll have particular numbers. Town A is A miles from the river. that's town 1. Town 2 is B miles from the river, and the horizontal distance here between these lines is C miles. S is the location of a pumping station that's going to pump water to these two towns. Okay, these are going to be two pipes from this pumping station to these two towns. Question is, where should you put the pumping station along the river to minimize the total length of the piping? Right? If you're the company, or you're the cities, they put their budgets together, they want to minimize the total length of the piping. They're sharing the cost. That would be a practical thing to do. Okay? That's why this is somewhat practical. Yeah, where should the pumping station be located to minimize the total length of the pipe? X is the variable that I want to find the total distance in terms of, and minimize with respect to X. I'm going to differentiate with respect to X. What do you think we need here? What kind of geometric fact do we need to help us solve this problem? We're trying to minimize the sum of these two distances. Here's a big hint. There's a right triangle there. Another right one here. I'm not going to write on the wall. What fact do you think we're going to need? It starts with a P. Pythagorean theorem, right? One leg squared plus the other leg squared equals the hypotenuse squared for right triangles, right? Don't use it for non-right triangles, only for right triangles. The length of that side of this right triangle is going to have a square equal to the sum of the squares of a and x, a squared plus x squared. So the actual length is the square root of that. Square root of x squared plus a squared. With this right triangle, the lengths of the sides are b and, well, if this is x and this is c, this is going to be c minus x from here to here. So that's going to depend on x as well as square root of c minus x quantity squared, which is the same as x minus c quantity squared, plus b squared. Although I think in the when I solved it, I actually did it as c minus x quantity squared, which may be more complicated than it needed to be. But on the next slide, I'm going to show you the solution. It's a lot of complicated looking equations. Okay, this is the slide with a lot of complicated looking equations. But again, just while you're in class here, don't write it down, just try to get the big picture. I already put this in the shared folder. What's the big picture? We got this function that we want to minimize. Unlike the example from Monday, we can't get rid of the square roots because we're adding two different square roots. If you tried squaring this thing, because of FOIL, the outside and inside terms would still involve, well, they would be still involve square roots because you'd be multiplying the square root of these two things together, and that doesn't make the square root go away because the things inside are different. X is the variable, but there are three parameters, A, B, and C, three constants. And I might be interested in knowing what happens as those constants change. Again, that sounds like an oxymoron, constants changing. But that's really what I'm thinking. What if the distances from the towns to the river, and what if that horizontal distance across the top change? How does it affect the answer? That's what's most interesting, most useful, because it applies to other situations too. Again, in your problem, you'll have particular numbers for A, B, and C. So your problem will be easier. But the method is the same. Can't get rid of the square roots, you got to differentiate this as it is. That is the first step, find the derivative to find the critical point. There's the derivative. Okay, don't write it down, just think with me here. Believe that you can do it. Square root of x squared plus a squared. Bring down the 1/2. That's x squared plus a squared to the negative 1/2 by the chain rule multiply times the derivative of the inside, which is 2x. The derivative of x squared plus a squared with respect to x is 2x. Right? No a squared or no 2a. Then add the derivative of that square root. You bring down the 1/2. You got the inside function. So the negative 1/2 multiply times the derivative of the inside function is this. If I had had an x minus c quantity squared here, then this would have been 2 times x minus c without an negative sign. It still should give the same critical point in the end. I need to set that equal to 0 and solve for x. Yikes! Really? Really, it's possible. Here are the steps. First, I wrote these things both as fractions now. I did 2 steps from here to here, essentially. I wrote these both as fractions. You got this thing to the negative 1/2. That's like dividing by the square root of that thing, which is what I got there. The 2's cancel as well, and there's an x on the top that comes from that x. And this thing I can write as a fraction as well. I can cancel the 2's again. I can put this thing to the negative 1/2 in the bottom as a square root, because it's a negative 1/2. And the negative 1 here goes away because I'm bringing this thing to the other side. I've got it on the other side there, with the c minus x on top. That's a nice way to have it now, because now it's a little bit more clear that if I square both sides, the square roots will go away. And so my next step is to square both sides, or maybe I cross multiply first. I guess I cross multiply first. I could have squared both sides first. So I multiplied x times that, and that will equal this thing times this thing. I cross multiply. You know, when you cross multiplying, you're really just multiplying twice. You're multiplying first both sides by this to make that cancel on the left. And then you're multiplying both sides by this to make this cancel on the right. Gives you the same answer as cross multiplication. That's an informal justification of cross multiplication. Now square both sides, the square roots will go away. You have to square the first x though, that gives you an x squared there. You also have to square the c minus x, that gives you a c minus x squared there. It does look a little bit better now because there's no more square roots, right? However, it does seem to be a downside perhaps in the fact that if you think about it, this is going to be a 4th degree equation. Maybe we'd have to use the computer to solve it. And I did use Mathematica to help me solve it, but it is technically possible to do by hand in this case. I think in this next step, I skipped a few steps. ... That's for you to fill in. Okay? On your own after class, do some work to check this. What happened? It's simplified to a quadratic. Really? Yeah, the 4th degree and 3rd degree terms will cancel. Okay? I'll leave that for you to check. It's worth checking. This will help you for your project. The 4th degree, 4th power of x and the 3rd power of x terms cancel, leaving you with a quadratic. And I like quadratics. Quadratic formula, yay! Really, with something that complicated? Yeah, oh, this is just beautiful. It simplifies beautifully. I didn't necessarily expect it would, but it does. I was amazed. I was so happy. And I could have made a mistake in checking this when I'm doing it by hand, but I used Mathematica to help me make sure I didn't make a mistake. Yikes, there it is with the quadratic formula. Take a second to believe it here. Your b term is the negative 2a squared c there in front of the x. That's negative b plus or minus the square root of the b squared is this. You get a to the 4th there when you square that. Minus 4 times the first coefficient times the last coefficient, constant term, all divided by 2 times the x squared coefficient. And amazingly, when you simplify this, the inside there, you get this, and you can take the square root of that. Square root of 4 is 2, all the 2's cancel. Square root of a squared, b squared, c squared is technically the absolute value of a, b, c. But because we're doing plus or minus, we don't have to worry about the absolute values. It simplifies quite a bit. It simplifies even more because if you try to factor the top as much as possible, you can factor out an A and a C from both terms on top and be left with A plus or minus B. And the bottom can factor as A plus B times A minus B. That's the difference of 2 squares. And then, when you take the plus there, you can cancel with the a plus b there, and if you take the a minus b here, you can cancel with the a minus b there. So, in the end, these are the two answers. And aren't they nice and simple and beautiful? I was so happy that I got it. Wow, that's amazing. Which one? There's two of them. Which one's the answer? Which one is the critical point we want? Probably that one in general, because that one's positive for sure. This one could be negative if A is less than B, like it actually was in my picture. To know that it's the right one, we might want to graph it. And I made a manipulate graph. I'll show you this, then we'll take a break. Down here further. Not that one. I thought I did. Oh, no, it's this section. Oh, I made an interactive map. Look at that. Isn't that fun? Woohoo! You can mimic my code to help you make interactive things. Where should we put the pumping station? To minimize the distance, I did make a graph of, oh, here's my algebra checking with Mathematica, but I did make a graph here. Enter the function first. And we see we got a minimum distance at a certain spot. That depends on A, B, and C, and it was the A, C over A plus B. And for a particular map, like in your homework, you should go through the entire process again. But once I've done this, you could plug in the values of A, B, and C just into that expression to get the minimum, the best value of X. And the minimum distance is when you plug that thing into the function. Right there, whatever that turns out to be. Maybe I should see what it is. Okay, kind of complicated. That's to be expected. Okay? All right, let's take a break.